Hi everyone! In today's video, we're going to be doing the first lesson of our energy and work unit. We're going to be going over the topic of conservation of energy. We're going to retouch on what a system is, and we'll start an introduction to work and do some easy practice problems with work. So, the first concept that we're going to be talking about is systems. So, a system we've already talked about in the first dynamics video, but we're going to be going in depth about it here. So, systems is what physicists used to solve certain types of problems. So, what a system is that it's basically just a small segment of the universe. For example, your room could be a segment, the earth can be a segment, the earth and moon can be a segment, and all of those segments of the universe is what we call a system. And where we've defined our system, everything outside of the boundaries of our system won't be considered when we're solving the problem. And this leads us to the conservation of energy. So, the conservation of energy is that energy is always conserved in a system. That means the amount of energy in a system does not change no matter unless an external force acts upon it. So, before we get into what external forces are and how they can change the energy of a system, some people confuse the changing the type of energy in a system as a change in the amount. So, for example, if in a system I have light, I have heat, and all of this through some process turns into mechanical, the amount of energy never changed, but the type of this energy did change. So now let's go into how we can change the amount of energy in our system. Okay, so we've talked about how a defined system won't have its energy changed unless some force outside of that system acts upon it. So, how does this occur? This occurs through a process that we call work. Work is not what we've typically defined in the English language. Work instead is the ability to change energy. For example, lifting up a box some distance means doing work. The correct mathematical definition of work is that work is equal to the dot product of force and displacement. The dot product basically means that work is equal to the force vector times the distance vector times the cosine of theta, and theta is the angle between force and distance. So it is the angle between force and distance vectors. So let's go over a couple of practice problems where I demonstrate how work can change energy in a system and how we can calculate it. Okay, so these first few practice problems are just going to be going over how to use this equation of force and the displacement dot product and how to read a problem and visualize it. So the first question says a 36 Newton force is applied to an object that moves 11 meters in the same direction as the applied force on a frictionless surface. How much work is done on the object by the force? Okay, so we know that we have a force vector. Let me change my color. We have a force vector moving to the right, and our displacement vector is also moving to the right because the object moves in the same direction as the applied force. Therefore, our the angle between these two vectors is 0, and cosine of 0 degrees is 1. So we simply have to do force times distance in this case. So work equals to force, which is 36 newtons, times the distance it travels, 11 meters, and plugging that into our calculator gives us 396 joules of energy. So I forgot to mention this initially, but the units of energy, the standard units, are what we call joules and can be represented with J. In this question, we have the same thing. A 36 Newton force is applied to an object that moves 11 meters in the opposite direction of the applied force on a frictionless surface. So, we have our force vector to the left. However, our distance is moving opposite to that of the force. That means our displacement vector is to the right. So first, you might think the degree between these two is 0, but remember that it's actually 180 degrees. And we know that cosine of 180 is negative 1. So our work will be equal to negative 1 times our force, which is 36 newtons, times the displacement, which is 11 meters. And this will give us 396, negative 396 joules. Negative work means that we're removing energy from the system. That means if our box started with some initial energy and we do negative work on it, we're removing energy from the system. However, if we're doing work and the work is positive, we're adding energy to the system. So the negative and positives of work is very important because it lets us know how the energy changes. Do we increase energy? Do we decrease energy? And from then, in more advanced problems, we will know what this energy can turn into. So this problem says a 36 Newton force is applied to an object that remains stationary. How much work is done on the object by the applied force? So this one's a little bit tricky when we first get into how to calculate work. So we do have a force, and that force is 36 newtons. But our box isn't moving at all. Our displacement is 0. So because we're not moving this box with this force, we're simply just pushing on it, the work is going to give us 0 joules. So this tells us that by pushing on the box in this case with 36 newtons, and the box remains stationary, that means that we're not changing the amount of energy in the system of what we call the box. So another way that you can think of this is when I first learned about what work was, I always thought that, let's say, we're holding a book up in the air. I always thought that means we're exerting some sort of energy. But actually, if we're holding a book up in the air, that book is stationary. Yes, we exert a force on it to cancel out the weight. However, the book is not moving. There's no displacement. So the work that we do on the book is 0. And that means that we're not changing the energy of the system that we call the book. So that's something important to keep in mind with work. It can get a little bit counterintuitive sometimes, but that's very important to keep in mind. So in this question, a 2 kilogram block slides 4.5 meters to the right on a frictionless table with a constant velocity of 5 meters per second. What is the net force on the block? So if we remember back from our dynamics unit, we always know that force net is equal to mass times acceleration. In this case, we're at a constant velocity. That means our acceleration is 0 and our force net is 0 newtons. Although the block is displaced, our force net that we're exerting on the block is 0 newtons, and therefore the work we do on the box is 0 joules. We aren't changing the amount of energy in the system at all. Okay, so this next question is pretty conceptual. A book of mass m is lifted upwards at a constant velocity, a displacement h, by a librarian. How much work is done by the librarian on the book? For the same scenario, how much work is done by the gravitational force on the book? So, if I have my block of mass m or my book of mass m, the forces acting on the book are the force of the librarian, which I'm going to call Fl, and the force of gravity, which is mg. We know that the displacement is upwards, so the displacement vector is up like this, and it's an amount h. Since this is at a constant velocity, we know that the net force is 0, so that the force of the librarian is also equivalent to mg, just in the opposite direction. Keep in mind that this is not asking for net force, for net work. If net work was asked, we can simply say it's 0 because net force is 0. However, this is asking for the work of each component. So we're going to have to take a look at the work done by the force of the librarian and by gravity, which is mg. So the work done by the librarian is equal to the force of the librarian, which is mg, times the displacement, which is h, and we know that it's positive cosine theta because it is 0 degrees, which means that it's positive 1. So the work done by the librarian is mgh, and the work done by gravity is the force of gravity, which is once again mg, times the displacement, which is h. However, the angle between the force of gravity vector and the displacement vector is 180. That means we have to multiply by -1, and we get negative mgh. And this tells you that because we know our net force is 0, we know that our net work is going to be 0 too. When we look at the work done by each component of the forces, we see that they add up to 0 joules, which is really cool. Before we continue with 2 last problems, I wanted to get into some helpful equations for using conservation of energy and work to solve these problems. So remember that when we define a system, the energy inside always stays constant regardless of what goes on outside of it. The only time energy changes is when a net force acts upon the system. Then we have an E prime inside. So what I like to do for solving problems where there is a change in energy is that I always look at a before and after. I always denote before as E naught. I know that E naught is always equal to E final when there is no work. If there is work, I know that I start off with E naught. And then I have this force acting on it, adding or taking away energy, which goes into our work. And when you add all of those together, we get our final energy of the system. So a good way to do this is always define your before and after of your problem. This is always before, or I like to use point 1, and this is always after, or point 2. And remember that this work can be negative or positive depending on what the problem is asking. So the sign of the work is inside the symbol. So that depends on the problem and the type of work done on the system. So let's do this last problem. You defined your system as your room. All the energy in your room adds up to 1,777 joules. Your room is cold and you decide to heat it. After a while, you discover that the energy in your room is now 24,500 joules. How much work did the heater do on your system? So we always know that we use the equation our initial energy plus the work that's done on our system will give us the final energy. So we already have our initial energy, which is 1,777 joules, plus the work that we don't know the heater did. And we also have our final energy, which is 24,500 joules. So simply, we just have to calculate the work by subtracting from both sides and plugging into the calculator. We see that the work done by the heater was 22,723 joules, which is a lot, but we were cold. Thank you so much for watching, and I hope this video was a great start to our work and energy unit. Our next video is going to cover the work energy and kinetic energy theorem, and we're going to be going over what kinetic energy is, what potential energy is, and we'll do a lot more with conservation of energy. Thank you.